Okay, so we have another example here, and we actually had a problem that had to do with this idea, and it was in the in-class materials from our very first week of class. It was just asking you to find a formula for the volume of this sort of configuration. So let's read through the problem, and hopefully you can recognize this problem from earlier. So the idea is that we have a piece of paper, a square, so a square piece of paper, 10 by 10 inches, and we want to form a box with no top by taking our square and cutting out, let me try to make it look more square. Cutting out squares from each of the corners and then folding up the sides. So we want equal size squares cut out from each of the corners. Like so. So we would take our scissors and we would cut off each of the corners. So the shaded part would be gone. And then once we do that, we would take our piece of paper and fold it along these dotted lines that I'm going to draw here. And then you can imagine each of these flaps. So this is a flap here, and then there's 3 more, folding each of those flaps up vertically. So if you're imagining this piece of paper lying in a plane facing you, you fold those flaps towards yourself, and you would form a box. You could just tape them together and form a box, right? So it would look something like this. Something like this, and it would have no top, right? So we would get something that has a volume, right? And we can figure out how to create the largest volume of such a box using basically the same procedure that we had, that we used in the previous problem. So what we want to do is first label everything that we're going to be dealing with. So we want to maximize the volume, right? So it does say here, we want as large a volume as possible. That means maximize the volume. And so that is something that we should definitely label with a variable. So we'll use V for the volume of the box. And then the other thing that we're going to need to label, the thing that might be changing, is the side length of this square. So I'll just use X for that. So we'll say that X is the side length of the cutout square. Okay. Now, okay. The other information that we are given in this problem is that we start out with a 10 by 10 square, a 10 by 10 piece of paper. And so we know that this entire length right here is going to be equal to 10, right? And so this is going to help us figure out a formula for the volume of the box, because the volume, remember, once we fold this into a box, this side length, it's not going to be 10 anymore because we've cut down the length. So this, let me start using some different colors to help us visualize this. So this length right here that I'm interested in for computing the volume of the box is going to be really just the length of this flap, right? So instead of being 10, it's going to be 10 minus the length of the cutout square, so that's X, minus another X down here. So it's actually going to be 10 minus 2X. That's going to be the length of the flap. So visualizing this after we've folded up our box, this length of our like rectangular cube type shape is going to be 10 minus 2x, right? The other way, so the other part of the flap, maybe I'll label this here in orange. This part is actually going to have length x. So if this is the length in green, the other height of the flap is going to be x, which we can see is this this distance right here. Okay, so try to take a moment to visualize this and see where these edges line up in your picture, and hopefully you'll be able to see that that would be the length of that particular side. And then since this is a square and we're cutting out a square from each side, we do get that the other length right here, it's also going to be 10 minus 2x, right? Okay, 10 minus 2x, and that would be this side right here. Since we start with a square and we cut out a square, it's going to be the same length. So putting all of this together, we can write down an equation for the volume of the box. So the volume is going to be equal to, we just take each of our sides and the lengths of these and multiply them together. So we get 10 minus 2x, another 10 minus 2x, and an x, right? So I'm going to go ahead and multiply this out. That'll make it much easier to take the derivative, which we'll need to do. So that will give us 100 let's see, minus 40x plus 4x squared, and then we'll need to multiply this by x. Okay, and so I'm going to go ahead and rewrite this in the normal order. So with our x cubed out front, 40x squared plus 100x, right? And so we do have our volume written as a function of the side length of the cutout square. Okay. Now, what we want to do is optimize. So we want to find the maximum volume that we can get. So, first let's just make a note of what the domain will be. So as is usually the case in these types of problems, 0 is going to be one end of our domain because the side length cannot be less than 0. So that doesn't physically make sense. So we need that x is greater than or equal to 0. The upper bound on our side length is going to be determined by the size of the piece of paper that we start with, right? So when we have we start with a 10 by 10 inch piece of paper, and so if we were to cut out, just imagine, the worst possible case is if we were to make our cutouts so big, so this is, like, say we were making really big cutouts and they were taking up most of the space, we could keep pushing these out more and more and more, and then in the end we would really just cut all the paper away and we would be left with nothing. And obviously that's not a good case scenario, but it is the upper bound for what x can be. So if x were equal to half of the side length, so half of 10, then the cutouts would take up the entire piece of paper and we would be left with 0 volume. So that would happen if x was equal to 5. If x was equal to 5, then these cutout squares would actually touch here, and then we'd be in that case where we get 0 volume. Okay. Now, so this is going to give us, since we've determined the domain, this gives us our interval on which to find the absolute max, right? So this is why we do this, why we determine what the domain is using the physical restrictions of the problem in order to figure out how to, or on what interval to look for the absolute max. Right? Okay, so the other thing that we need is the critical points of the volume. So to find those, we take the derivative of v, and this will just be the power rule. That will be 12x squared minus 80x plus 100. And to find the zeros of this, we're going to want to factor it. So it turns out we can pull out a 4. So first we should just go ahead and pull that out before we try to factor this further. We'll be left with 3x squared minus, here we get 20 plus 25, right? Okay, and then let's go ahead and factor this further. So what we want is something of this form, right? And we will need a 5 and a 5, and so that doesn't, so that fills in a lot of information, and then if we just make both of these negative, we should get negative 20x when we multiply this out. Okay, so if we set this equal to 0, we will be able to find our critical points. So that will happen if 3 minus 5x equals 0, or x equals 5. In this case, we would get x equals 5/3. Okay, so our critical points are going to be, so it's not strictly necessary to rewrite this, but just so this is clear, our critical points are 5/3 and 5.